The James Webb Space Telescope, commonly known as JWST, has dramatically expanded our understanding of Pluto, transforming it from a distant, frozen relic into a surprisingly dynamic and complex world. For many years, Pluto was thought to be nothing more than a cold, inert rock on the fringe of our solar system, made primarily of rock and nitrogen ice. But recent observations from JWST have challenged that perception, unveiling a world with active geology and potential habitability far beyond what anyone had anticipated. One of the most groundbreaking revelations is the strong evidence for a subsurface ocean beneath Pluto's icy shell. This discovery suggests that Pluto may not be geologically dead, as previously believed, but instead an active world with internal heat and ongoing processes. At the center of this revelation is the heart-shaped region known as Sputnik Planitia. Once assumed to be just a frozen plain of nitrogen ice, this area is now believed to conceal a vast underground reservoir of liquid water. Scientists think this hidden ocean could be kept warm and stable by the slow decay of radioactive elements deep within Pluto's rocky core. This places Pluto in the same intriguing category as moons like Europa and Enceladus, icy worlds orbiting Jupiter and Saturn that are also believed to harbor subsurface oceans. These bodies are now seen as prime candidates in the search for extraterrestrial life. The presence of liquid water so far from the Sun challenges long-held beliefs about where life might emerge. Traditionally, astronomers focused on the so-called Goldilocks zone, the region around a star where conditions are just right for liquid water and life. But Pluto's hidden ocean suggests that habitable environments could exist well outside that narrow band. Could microbial life exist beneath Pluto's icy crust? The mere possibility forces scientists to rethink the necessary conditions for life. If life can arise in the dark, pressurized waters of Pluto, it could be far more common in the universe than we imagine. JWST has also captured detailed evidence of geological activity on Pluto's surface. Despite its immense distance from the Sun, Pluto features towering ice mountains, deep canyons, and expansive smooth plains. These features suggest that the dwarf planet's surface is constantly evolving. Unlike Earth, which relies on a molten core for tectonic activity, Pluto's reshaping may be driven by convection within its thick layers of nitrogen ice. Warmth from the planet's interior causes the ice to slowly churn, continually refreshing and altering the landscape. Pluto's interaction with its largest moon, Charon, adds another layer of complexity. Unusually, Charon is nearly half the size of Pluto, and the two orbit a shared center of gravity located outside Pluto's surface. This unusual gravitational relationship generates tidal forces that may produce internal friction and heat, possibly contributing to geological activity on both bodies. Charon itself is fascinating, marked by massive canyons and a reddish-brown hue. Scientists suspect this coloration is caused by tholins, complex organic molecules created when ultraviolet light strikes methane. There's even evidence that material is being exchanged between Pluto and Charon, possibly transferring organic compounds essential for life from one body to the other. This kind of exchange opens up new ideas about how life's building blocks might spread across the solar system. It suggests that life, or at least the ingredients for it, might travel between planetary bodies through natural processes. Pluto's atmosphere is no less remarkable. Primarily composed of nitrogen with traces of methane and carbon monoxide, it undergoes dramatic changes as Pluto travels along its elliptical orbit. When closer to the Sun, Pluto's surface ice sublimates, transforming directly from solid to gas. As the planet moves farther away, the atmosphere refreezes onto the surface. This cycle of vaporization and recondensation is unique in the solar system. JWST has even detected haze layers stretching hundreds of miles above Pluto's surface, evidence of complex chemical reactions happening in the upper atmosphere. These atmospheric processes could be critical to the development of prebiotic chemistry, the early chemical steps toward life. If Pluto's surface or its concealed ocean hosts such chemistry, it could provide clues about life's potential elsewhere in the universe. On Earth, deep-sea hydrothermal vents support entire ecosystems, thriving not on sunlight, but on chemical and thermal energy from below. Could similar environments exist under Pluto's ice? If so, even the discovery of simple microbial life there would revolutionize our understanding of biology and habitability. It would prove that life isn't confined to the warm inner regions of the solar system but can emerge in the most extreme and unexpected places. While the James Webb Space Telescope has given us remarkable insights, a dedicated mission to Pluto is essential to verify and expand upon these discoveries. Scientists are currently discussing proposals for orbiters, landers, and even robotic submarines. A probe equipped with ground-penetrating radar could map the extent of Pluto's hidden ocean. A lander could analyze surface chemistry with high precision. And one day, a nuclear-powered submarine might dive beneath the ice to search for signs of life in the dark waters below. Pluto, once dismissed as a frozen outcast, now stands as a frontier of possibility. A small world that may hold answers to some of the biggest questions humanity has ever asked. Are we alone? And what, exactly, does it take for life to emerge?